team, and I came here to talk about, Stratus, which is a private cloud we built for self-managed research computing, and some of the reasons we decided to build this and some of the things we went through in the process. It's built on OpenStack using Ceph storage, and we built it to fill certain gaps in our HPC service offerings, but still wanting to give our end users HPC-like performance. And, well, like the slide says, we also wanted a flexible environment to handle our future needs. So to dive straight in, this gives kind of an overview of Stratus. And one of the main things we built it around, though not the only thing, was we wanted a safe space for processing controlled access data. And so to that end, we built it as a kind of walled garden, isolated from MSI's other core services. There are two ways for our users to access it. One is through a pretty standard Horizon web interface, and then we also have an SSH Bastion host. Both of these are set up with two-factor authentication using the university's single sign-on, using Duo as the second factor. And most network access into the tenant networks is blocked by default, with a couple of exceptions. So the Bastion host is also the way users will gain access to their virtual machines via SSH, and it's also where they can use the OpenStack API. So we built 3 types of storage into Stratus, all of them using a Ceph backend using full disk encryption. And the first of these is pretty straightforward, Cinder volume service using RBD. And then we built 2 tiers of object storage. The first of these we called the S3 cache, and it's kind of designed to hold large controlled access data sets from outside institutions. So as well as having the capacity to hold these data sets, it's also subject to a bucket lifecycle policy so that it purges old data after 60 days. Then we also have the second tier, which we call S3 secure, which works pretty much the same way, except there's no lifecycle. So that's where people can store controlled access data in a more persistent manner. Then, while most of our other services are blocked from Stratus, the users also have access to our general purpose S3 store, which is a separate Ceph cluster of about 4 to 5 petabytes. And that's where they can put open access data, maybe including results derived from their workflows on Stratus. So before going any further, I wanted to give a really brief outline of MSI. It was founded in 1984 using the university's Cray 1 supercomputer at the time. Right now we have 42 staff across 5 groups. That covers operations, user support, application development, and a couple of consulting groups for physical and life sciences. We have about a little more than 4,000 users across 700 research groups, not just at the university, but also private and public entities across the state. And the traditional focus has always been on batch job scheduling. Now, while we have some kind of more interactive systems tied into that, most of the workflows run on our 2 big HPC clusters. And you can see some details of our newer one called Masabi in the sidebar there. And most of the workflows fall across a spectrum of 2 kind of types of computation. You have traditional HPC, usually associated with the physical sciences, where you have a lot of processes, very computationally intensive. All the processes are communicating continuously using message passing, or MPI. And then at the other end of the spectrum, you have what you might call big data, more associated with the life sciences, though not necessarily high energy physics analysis would fall at that end of the scale. Also computationally intensive, but the processes don't need to communicate with each other. And this tries to give kind of a breakdown of how allocation and CPU time and storage falls for discipline. And you can see that the life sciences only consume about a quarter of our CPU cycles relative to physical sciences. This is traditional HPC. Yeah, this is the statistics out of the main clusters. So yeah, the physical sciences consume most of our CPU, but only about 1/3 of the storage capacity. So as well as this environment for processing controlled access data, we had a number of other reasons we wanted to address, or use cases we wanted to address. The first of these was what we've been calling on-demand computational resources, which is kind of a catch-all for workflows that are or could fit into the batch processing system. So they might be more interactive in nature. You know, users can request interactive resources in the HPC cluster, but depending how big the request is, it might be hard for that to get scheduled, especially outside of off-peak hours. Then there was more demand for self-service computing, by which we mean an environment where the users have direct control to set up the environment, maybe with containers, but in particular, they need root access to build the environment they need. And finally, we wanted to satisfy a need for long-running jobs, because the HPC clusters have a monthly maintenance schedule, which involves draining the queues, putting jobs on hold while we perform maintenance on the system. And so the longest job that people can run tends to be 29 days or so. So for the controlled access data, we had a particular use case in mind. It was dbGaP, which is the National Institute of Health database of genotypes and phenotypes. And we'd had an increasing number of researchers coming to us wanting to work on this kind of data. We have over 40 research groups working on dbGaP at the U. And broadly speaking, it's non-identifiable human genomic data intended for bioinformatics research. So within dbGaP, the data is classified into open and controlled access. And the controlled access data is governed by the genomic data sharing policy. And the requirements of this tended to be kind of hard to fulfill on the HPC clusters. So for example, two-factor authentication was one requirement. And we tried to address some of these on the HPC cluster, for example, by building a separate login node, which gave two-factor authentication. But there was no way for us to force the users to only use that means of access. There would have been side effects that made they lost access to all kinds of other resources. And at the same time, we were able to make a special volume on the global file system, which was exempt from backups and snapshots. But still, there was no way to handle encryption at rest there. So, we just couldn't really meet the needs on the main HPC cluster. And this slide tries to give some impression of the explosion in size of this type of genomic controlled access data. The plot's actually given in petabases, but you can get a rough estimate of our version of data size by dividing by 4. So we think there's probably around 8 petabytes or so by now. And this fed in a lot to the kind of dbGaP cache model for storage within Stratus. Because, well, for one thing, we didn't want to have to store 8 petabytes. We weren't ready to go to that kind of scale. And we're also not an NIH trusted partner, which is what you need to hold a persistent copy of the data. That wasn't something we wanted to, a path we wanted to go down at this time. So as Stratus was being considered as the solution to these problems, there was a lot of kind of debate internally about whether we should be the right home for this kind of project. IT at the university is somewhat decentralized, so while we have a central Office of Information Technology, many of the colleges have their own IT teams, and MSI itself falls under the Office for the Vice President of Research. So while we provide services to the U as a whole, we're not part of central IT. So in the context of controlled access data, for example, our academic health center has a lot of experience working with controlled access HIPAA patient data, for example, but not in the context very much of research and not with a lot of computational resources attached to it. And central OIT also handles a lot of, FERPA student data, but again, no research aspect and no computational aspect. So it's kind of clear that MSI was the right place to handle this, but we had to go through a kind of discussion period of how we were going to evolve to meet this expanded need. So there was a certain amount of culture change needed. Everything we did was based around providing these fully managed HPC services where you don't really trust the users very much. And there was a lot of fear that self-managed VMs might undermine our infrastructure security. And so we went through a bunch of kind of therapy sessions internally where we could figure out the best way to handle the security requirements for this new type of environment. And then finally, it was a big shift for us to really be actively soliciting this controlled access data, where at best it had been discouraged before. So we kind of addressed that by having a very specific focus on the requirements for dbGaP and not getting sidetracked by, what about HIPAA, for example. So Stratus kind of became a real project, and this shows the timeline we came up with, as well as some of the staff resources that were ultimately assigned to it. We had a team of about 7 people representing a little under 2 full-time equivalent staff time. And, well, for the timeline, I guess we originally envisaged it to take about 12 months from start to end in production. In the event, we had kind of an extended period with our internal friendly users, and it took more like 18 months. So one of the first things we did was build a development cluster. So we could kind of kick the tires on OpenStack, as it were, and develop our kind of vision for hardware requirements. So the OpenStack component of this we built from a chassis, kind of liberated from our older HPC cluster. That's labeled Stratus Dev in the picture. Then the Ceph side we built from, we had repurposed hardware from an old Lustre storage system, which we kind of threw together, and it was named Frankenceph because no one really believed it could live more than a day. And they were wrong, A little later, it was joined by the lovely bride of Frankenceph in the next rack over, but that's another story. So, this cluster gave us a bit of experience in putting together OpenStack, configuring it, and we also did some testing of deployment, a more kind of managed deployment using Puppet OpenStack. And one of the big things we wanted to test was if we could get something we could call HPC-like performance. And having the hypervisor hardware be identical to our older HPC cluster was pretty useful for that. It gave us a one-for-one comparison. So the development cluster gave us the idea we were on the right track. So we had to decide what the production system would look like. And we kind of thought about a large variety of options. And the plot here sort of attempts to show how we scored some of the options based on 6 parameters: performance, scalability, storage, size, ability to customize, cost savings, kind of just an inverse of cost, and ease of operational effort. And we started out looking at some pure cloud solutions. I think we looked at AWS, Azure, Rackspace, maybe. And we concluded that we could probably get any level of performance and scalability we wanted, but the cost would probably be higher than we could stomach. And we also had discomfort with this data being offsite. And then we also solicited some proposals from vendors for kind of turnkey Ceph and OpenStack systems. And it was kind of clear that there were a lot of limitations to how we could customize these while staying within their support parameters. And it seemed that would interfere with some of the things we wanted to do for security. And also, they were really targeted to enterprise workloads, very high CPU oversubscription, not really designed for HPC performance. And you know, they just weren't going to be cost effective at the scale we needed. We weren't actually going to get that much hardware in terms of cores or storage for our money. So, you know, based on our experience with the development cluster, we decided we'd build our own system, develop our own in-house expertise, and we could be free to customize it as we needed for our own security and performance requirements. And this is the design we came up with. We built the hypervisor side out of 20 compute nodes, pretty much identical to in the Misabi cluster. And that kind of came out of part of our risk acceptance for the project, because you know, if it was a disaster and didn't work out, these could then be merged into the main HPC cluster with no real loss. Then for the storage side, we built it using these HP Apollo 4200 storage nodes, which were very dense systems holding like 24 full-size hard drives and 2U, as well as a variety of SSDs and NVMe cards. We tied it together with 2 40-gig network connections per storage node, 2 10-gig Ethernet to each hypervisor node. Then beyond that, we also needed some number of API, accessory nodes. And we cunningly dedicated all of our money to the hypervisors and storage. So luckily, we found we had some hardware we could repurpose from other projects for, the OpenStack services, Ceph mons, gateways, so on. And we did some minor upgrades on those of CPUs and things, which I subcontracted out to my 10-year-old son at the time. And everything is still working, so he did a pretty good job. This tries to give kind of an overview of the OpenStack architecture, and you can see it's really a pretty minimal set of OpenStack services. We have Horizon and Keystone tied into the university's Shibboleth identity provider, and Nova Compute Services, Neutron. We're using distributed virtual routing, VXLAN overlay networks, Cinder and Glance volume and image services using the RBD volume backend, and it's kind of orchestrated in a way using the Puppet OpenStack modules. And that was kind of chosen because we had a long-standing history with Puppet within MSI. The storage system was built out 8 of these HP 4200 nodes, and we based the hard drive storage using NVMe flash for the journals, file store, and divided up into 200 gigs of block storage using 3-way replication, 500 gigs of object storage using 4.2 erasure coding. And we also had a SSD pool to hold the object store indexes and kind of some spare high-speed block storage. We were able to go through a long phase of configuration testing using CBT, the Ceph benchmark tool, to measure a bunch of variables we could change. So the plot shows like the performance of BlueStore versus FileStore, and BlueStore actually looked pretty promising. This was probably in late 2016. So we did actually run into some issues at the time with BlueStore. We decided to deploy using FileStore at the time. There are also other interesting parameters to measure, like the FileStore split merge thresholds, and finally I'll mention we were able to measure the impact of the full disk encryption, which was less than 1%, so we were pretty happy with that. And so we wanted to, I said we wanted to offer HPC-like performance. And so we ran various benchmarks on the system. The one I'm going to focus on is HPL, which is high performance LinPack. It's a really popular measurement of HPC hardware floating point performance. And it was probably one of the most important parts of the acceptance tests for Misabi. So the plots show, the blue and the red lines at the top can show peak performance of Misabi versus a Stratus virtual machine for weak scaling. There's two types of benchmark there reflecting different models of the benchmark. Strong scaling, kind of you take a problem of a certain size and then you divide it successively between cores. So as you add more cores, the problem assigned to each core becomes smaller. And you can see That's the sort of yellow and green plots. You can see the performance kind of tails off because it's becoming more dominated by communication overhead and I/O. With weak scaling, you take a problem size and then duplicate it across cores as you add cores. So it's really more of an idealized, efficient model. Anyway, we could see that we got less than 5% performance impact from virtualization. And this was, we had some tuning options disabled, CPU pinning and NUMA. We wanted to keep the option for live migration available, and those would have interfered with that. We have hyperthreading enabled, and we also had like 2 times CPU over subscription enabled, though that's not reflected in the benchmark results. Storage was really way harder to measure, and unlike the Ceph initial tuning where we could vary one parameter and get really definitive results out of it. In this case, we were really trying to measure the global parallel file system on Mesabi versus block storage on Ceph, and they're really very different beasts, have very different performance characteristics. And the quote, we claim that file system benchmarking is actually a disaster area full of incomplete and misleading results that made it virtually impossible to understand what system or approach to use in any particular scenario. That actually spoke really directly to us. But one thing we knew we had to do was tune the quality of service IOP limits for Nova to provide kind of a comparable performance to Mesabi. And so we selected FIO with random IOPS, which, based on some research, seemed like the closest match to typical user workloads. And characterized the performance for Mesabi, and then dialed in suitable like IOP rate limits on Stratus to kind of match. And we selected this RBD 800 in the end, which is 800 IOPS. We got really different times, different performances out of the Mesabi global file system, depending which volume we happened to test and what time of day. So there were a lot of variables at work here. Stuff performing the benchmarks kind of provided a preview of the experience our users might find, because our benchmarking specialists, they're not systems administrators, they're people of refinement, and we dropped them into this completely unmanaged environment where, for the first time, there was no home directory for them to keep their scripts and results, no batch scheduler to coordinate tests between different systems, and they had to install their own software. So that was an interesting time for them, and it really fed into when we were bringing in our first users. Based on that and some of our other early users, we put together kind of a bare minimum tutorial to give them some basic introduction to OpenStack, how to provision VMs, attach storage, and some basic systems administration. Once you have a volume, you have to create a file system and mount it. So on. We got the same questions over again. Where's my data? Where's my software? How do I submit my jobs? And who do I ask to install software? The answer is you. It's a self-managed system. So to ease their way in a little bit, we did create a set of pre-configured images, starting with what we call the dbGaP blessed image. It's based on CentOS because we're kind of a CentOS house, I suppose. That was preloaded with some of the data transfer tools. They'd need to pull data out of dbGaP and perhaps put it into the S3 cache, and an assorted catalog of other tools that were commonly used in their field. And layered on top of that, we made 2 further images: a remote desktop image, which was pre-configured to have appropriate security controls, and also Galaxy, which is a web-based tool really widely used for computational workflows and biomedical research. This slide tries to show some of the controls we put in place for security. And on the left, it shows the controls we put in place for MSI's infrastructure. But in addition to that, we wanted to put some kind of bare minimum sane defaults in place for the user environment, which goes beyond what you might get from a standard cloud provider. So, for example, this is one example of network isolation. The only 2 ports open from campus are HTTP and RDP, both with SSL required. Anything else had to go through the Bastion host. And as well as that, we put some ACLs into place on the core switching within Stratus, which prevented any traffic passing between separate tenant networks. So from the beginning, we wanted Stratus to be a paid subscription service, both to discourage superficial users and to encourage responsible resource usage. And during development, we tinkered with some of the components OpenStack might provide for this kind of thing, Noki and CloudKitty, but this was probably still late 2016, early 2017. We didn't feel they were quite ready for prime time, and maybe we weren't quite ready for prime time either to make best use of them. So we settled on a straightforward, simple annual base subscription using, a base subscription, 16 CPUs, 32 gigs, 2 terabytes block storage, with some a la carte add-ons. Being the university, it had to be zero profit, but we were able to build in our staff FTE costs. And we performed a basic cost comparison with AWS, pre-buying similar level of infrastructure for a year, and we found our costs to be about 11 times less. This is costing us for internal university owners, though. We don't take outside users. So with Stratus in production and bringing users on board, we started to find out all the things we didn't necessarily expect. So the very first thing, on the first day, our very first group requested to buy an extra 20 terabytes, 10% of what we'd provisioned in the first place. So it really brought home how accustomed people are to the convenience of POSIX storage. And object storage is still really alien to a lot of people. And so they were really happy to just pay for the convenience. It was a surprise because we expected our users to be more cost averse than they were. And then the next thing we found was we needed to add extra layers of support. We started with just a basic ticket system. Our operations people won't actually log into the VMs and change anything or do anything, but we would provide basic triage and advice about things. But some users were fine with that. We never heard from them again, other than things are going fine. But some needed more help. And so some of our groups have engaged in paid consulting from the operations group, either to set up or tune the infrastructure, and some are contracting with our research informatics group, either to help them develop workflows, advise on the best software packages to use, or in some cases to build a virtual environment and perform the entire analysis. We also found that demands on the resources came much sooner than expected. Earlier this year, we had one new research group join us who are working on whole genome data, TopMed, which is 100 times larger than the exome data that other users had been working on. And if the inset kind of goes back to the plot of the increase in storage for genomic data, and that spike in 2016 was when the TopMed project was ingested into dbGaP. So these users are used to running on 1 terabyte scale HPC cluster nodes, and within Stratus, they're running multiple VMs with 50 cores and 100 to 2 gigabytes of 200 gigs of memory each. So this is fed into our plans to expand sooner than we might have expected. All our users asked for a more flexible subscription model, so we changed it, for simplicity, to a quarterly model. I'm sure we'll come back and revisit CloudKitty in the future. And then finally, our first 6 to 8 months of operations were devoted purely to the dbGaP users, but we did have these other use cases we wanted to address, and so in February this year, we created a new provider for these general users. And it's separated from dbGaP by being based on a separate provider network, and the main differences are it has open access from campus IP space, but loses access to the Stratus secure object stores. Then, I wanted to try and go through a few conclusions and then think about some of the directions we might want to head. Did we make a good decision? Well, for MSI, the issue of providing an environment for this controlled access data was something we definitely had to address. And I think it's given us a solid starting point, and we can build on it to expand to other types of data, such as FSMA or FedRAMP, as needed. For the users, it's providing the performance and security and flexibility that they need to build their environments, but there's definitely a range of success in their adaptation to this. Their lives are definitely more complicated. I guess adding our extra levels of consultation is going some way to leveling the playing field there. And would we build it the same way again? Well, clearly, the vendor solutions really wouldn't have given us a scale that would be compelling for our users. We wouldn't have been able to bring in the top med, large-scale users with that scale. And also, would we use OpenStack? Well, the strength of the community has been a great asset. There's people working in every possible problem space and overlapping with our interests. I think if we changed anything, we'd be questioning the S3 object cache because, we thought it was a really elegant technical solution, but users are pretty reluctant to touch it. In future, we definitely would like to bring in Barbican to manage user encryption keys. The whole disk encryption behind Ceph isn't necessarily addressing the specific needs of dbGaP. They want data to be encrypted using the user keys. And so we were recommending that they should use their own encryption within S3. And the MinIO client supports server-side encryption now. It's actually pretty easy to use. But a key management system would definitely make that more transparent. And also, we're seeing people are reluctant to use object store. They want to create POSIX storage. And so, Barbican would make providing encrypted volumes much easier. We've had some interest in different types of nodes, either for large memory or GPUs. Virtual GPUs were going to be really interesting once we get to Queens. A lot of our users would be really interested in some kind of shared storage between multiple VMs. And so, multi-attached volumes might go some way to providing this, but it's read-only, so I'm not sure how much use there'd be made of it. Some kind of storage as a service using Manila and NFS would probably be really popular. And building on top of that, a lot of our users struggle with the lack of job control. They're used to having a job scheduler to protect them from over-allocating resources. In some consultation cases, we've logged into a VM and found 3 times more processes running than there are cores in the VM because they've started things in background, gone away, started more things. So some kind of HPC as a service, like maybe providing a really simple Slurm scheduler would probably be nice for those people. That brings me to the end, so if there are any questions?
For your dev system, what was the interconnect?
For which system, sorry?
For your development system?
Oh, right. Yes. Well, I didn't talk about I/O for a good reason on that, because it was using gigabit Ethernet.
The second question in relation to your dev system, did you engage with any of your user research groups? And which areas of research, which areas of, were they, if you did this, or did you do this, and which ones were the most interested to get on board and get involved?
The most interest was kind of, I don't know if it was coming from the dbGaP users, but it was partly a push from MSI because the environment within the main HPC cluster wasn't really working out and wasn't really meeting the requirements of the data. So, we did engage some of them in the concept. Yeah. So. Yeah.
Would you, given your experience now, would you consider down the road going to a unified solution also for the rest of HPC?
Oh, right. You meaning
as one big OpenStack?
Something like Bridges and Ironic, maybe? Or yeah, I mean, but certainly kicking the idea around. This is a really small system to be imagining that scale up. So I'm not sure what the feeling is there, but we definitely want to start experimenting with Ironic as well to see, where we can go with that.
Where do you see the NX advantage versus AWS coming in? Do you see that as a sustainable thing going forward, or do you think that will go away in the future?
The advantage of,
The cost savings.
right. Yeah, I mean, obviously, the cost savings are the books are a little cooked since it's basically infrastructure cost, and our cost is not really built into our numbers there, though it is built into the cost recovery model. Yeah, I think we definitely have use cases where we're looking at bursting jobs into AWS and other cloud providers, so I think there's going to be some ongoing crossover there.
But do you see that as a sustainable thing for the next year, 2, 3, or is that going to go over the next year?
I think we expect to continue building on Stratus for the next 2-3 years, for sure. Do you want me to point? Can I?
Do you have any problems sharing GPUs amongst the users? And if yes, how do you address it?
At the moment, Stratus does not contain GPUs, so that's something we'd like to look at further on this year. Our GPU users right now are all in Miss Abby, in the main HPC cluster.
Did you or are you planning to look at satisfies for any of your use cases?
Definitely. We've been interested in satisfies for a long time, and we've done some really basic level experimentation. I'm not sure how it fits into this particular model. Obviously, when we were talking about storage as a service, satisfies plays a role in that, via Manila. But I think we'd be reluctant to expose the Ceph infrastructure directly to the user VMs. But we're definitely really interested in looking at Ceph for general purpose scratch storage in the non-protected space, perhaps based on a separate Ceph cluster.
When you talk about object storage and then you refer to S3 cache, do you mean OpenStack suite or?
No, this is S3 from Stratus Gateway in Ceph using S3 protocol. At the back. No, it's pretty much self-certified. So we have to, review ourselves every year and make sure we're addressing the requirements.
Couple of questions. What about your networking requirements at scale in terms of having, SDNs, a specific SDN brand or any kind of, strategy at real scale?
Right. Well,
The other is if you're using cells.
no, not yet. We're running Newton still, so this summer's going to be a real upgrade treadmill, I think. And the system's really too small for us to have needed to go down any very complex SDN requirements. So yeah, I don't really have anything to say on that. Sorry.
How did you have to evolve the skill set in the last few years, and how do you see that going forward?
Right. Well, it was a big change for me. I kind of joined MSI right at the beginning of this project, and at that time, I'd been building clusters and storage systems for mostly high-energy physics groups at the time, and OpenStack I'd never touched before, Ceph I'd never touched before, Puppet I'd never touched before. So, at the beginning it really felt like trying to perform brain surgery wearing welding gloves or something. And I mean, it took a long time to become remotely comfortable with feeling you had any clue what was going on, to be honest. But I think kind of hit a good part of the learning curve now, so I think we'll be able to continue on pretty successfully.
What is the ongoing support burden for this? How many FTE are you using to support this cluster?
Oh, day to day, I think we've been kind of, since going into production, it's been running in a fairly stable mode, and we're going to be ramping up again to go through the Newton, Okada, onto Queen's upgrades. I think the support burden will increase a lot for that. It's probably 10% of an FTE or less, I would say, in terms of maintenance at the moment. But I think it'll be a lot higher this summer as we push onwards. Can I?
So for your traditional HPC environment, is that allocation based? Is it only use or is it? How does it compare in terms
It uses SUs, service units, which are they're not paid in any way. They're free for anyone at the university to use with a base allocation, and then yeah.
and then, so how many groups, like, you're just catching the special cases that could be captured?
Right, this Stratus at the moment is meant to be complementary to the main HPC clusters.
The system size, you're like doing 10 research groups?
I think we've got about a dozen dbGaP groups onboarded at the moment, and maybe 4 to 6 like general purpose cases. But they're not doing heavyweight research. Heavyweight, compute jobs.
Sorry, one final question.
Sure. Yeah.
You came to the conclusion of making research like environments, like pre-designed images for specific use cases. You just gravitated towards the two, like running traditional?
I think the blessed image is, I think, evolving into a more general purpose image based on feedback from the research informatics group. So it's still mostly targeted at the bioinformatics researchers. We haven't really made any images targeted to other users, other types of research at this point. Yeah. Anything else? Oh, sorry.
Blessed images, what's your method for keeping these up to date and redeploying? And it seems that you're counting on your users to take them, build them into their own tenant networks appropriately. Are you counting on them to do this securely and in the right way?
Right, yes, there's a definite part of the training or introductory tutorial tries to go through the shared responsibility model for security. Once they build a VM on a given image, it's kind of static unless they update it. Perhaps one of the things you're thinking of. We build new versions of the image regularly. Our expert on that is sitting in here. Uses Disk Image Builder to create new versions of those. But once a user's provisioned a VM from an image, they have to update it themselves. And it's, what can I say? We've tried to make it clear that that's something they are expected to do. While at the same time, we've walled them off, just in case they don't. Anything else? Well, thanks very much. Yeah.